So this is going to be a tutorial for how to do confidence intervals, as well as just thinking about the distributions of sample means and sample proportions while in Excel. So the very first thing that I have here in the file is or the first worksheet is known standard deviation and proportion. So I've got this data. It's got male undergraduate, female enrollment, total undergraduate, and then an indicator for whether or not that school had a number of undergraduates over 10,000. So 1 if they did, 0 if they didn't. So the very first thing we could do, and hopefully we're all pretty familiar with this by now, is look at that total number of undergraduates and just find the mean of it by using that average function in Excel. Next, we could find the variance, treating this as the population because this data set has every Division I school in it, so we're using that var.p to find the variance. So we now know that we've got the population mean and the population variance. Okay? So let's say we took a sample, right? This is the population data. Let's say we took a sample and found that the sample mean was 20,000, right? And that sample was of size 111, okay? Using that norm.dist function, well, if we now have the cutoff value of 20,000, we know the population mean, and then we know the population variance, but in Excel we have to tell it the standard deviation. So we take the square root of that variance, and then we said the last option, comma 1, tells it, find me the probability of seeing 20,000 or anything to the left, right? So that's how we would find the probability of seeing any one sample mean value. We also could find the mean proportion here. So this is a 1-0 variable, and so if we wanted the sample proportion from this sample of data of schools that had graduates over 10,000, taking the average of a binary or a 1-0 variable, that is a proportion. So mean proportion, or however we want to call that, sample proportion, all we have to do is use that average function to find the mean of that 1-0 variable, and that will reflect the proportion to us. We've got our sample size of 111. That was just using the count function. That's always how we found the number of observations that we had. So if we go down here, right, and let's assume, right, that this was population data up here. Even though this is our sample, I'm giving you an example where we have a known standard deviation because sometimes that could be the case. Okay? So the very first thing we need to do is find what z-value we need to construct the margin of error for the confidence interval. So we've got a lower bound and an upper bound that we need to find, but in order to do that, we have the equation that we take the sample mean that we found, and we then go to the right and the left of it some amount. That amount would be what we're calling the margin of error, and to determine what the margin of error is, it depends on what confidence level we want, and depending on the confidence level we want, we'll look up different z-values and then multiply the standard deviation of our sample means, which the equation for that is the square root of the original population variance divided by the sample size that we took. Okay? So how do we find those z-values? Well, for our confidence levels, we said if we have confidence levels of 90, 95, or 99%, those would correspond to alphas of 0.1, 0.05, and 0.01. The confidence level is essentially what proportion of the sample means will be within this confidence interval. So if 90% are within it, then only 10% would be outside of that confidence interval, and in decimal form, that would be an alpha of 0.1. So once we have these alpha values, I just set them up like this, and we'll delete this here so I can show you how this was constructed. We'll take the norm.s.inv function, because we know that we want to get a z-value that gives us 0.1, right, outside of our confidence interval. Well, if a confidence interval has a side on the left and a side on the right, the area outside the confidence interval is 0.1, then there must be 0.05 on each side. So we want to find the z-value that if we look to the right of the positive z-value or the left of the negative of that z-value, we'd have 0.05 or half of our alpha on each side. So when we'd add them up, we'd have the alpha of 0.1. So what I'll do is I'll take my alpha value and I'll simply divide it by 2. Right? Now if I just do this, it's always going to look, this norm.s.inv always looks at the area to the left. So I'm saying, okay, what z-value would give me 0.05 to the left? Well, that's a really small area. It's going to have to be something that's very far to the left of the mean of our z-score distributions, which the mean is always, we know, 0. And so we're going to get the negative z-value, but in the equation for confidence intervals, the lower bound takes that negative z-value, the upper bound takes the positive. So we just want to be dealing with the absolute value of this z-score. So the function in Excel that allows us to do that is this ABS function. Right? So we can take the absolute value, and that will give us just the z-value that would give us 0.05 to the right. Right? So we go ahead and do that. We can copy this down because the cell reference for what alpha is, we want to look at 3 different confidence levels: the 90, 95, and 99% confidence levels. So we copy this down. Right? The next thing we need to do is construct our lower and upper bound. So we always build our confidence interval around whatever sample mean that we found. So we click on that sample mean. We'll then subtract the z-score for the confidence level we're interested in, multiplied by the square root of the population variance, in this case, divided by our sample size. Okay? So once I have this set up, if I want to copy this down, one of the main problems is going to be all these references update. And the only thing I really want to change to build different confidence levels is that z-score. The sample mean isn't changing, the sample variance, the sample size isn't changing, only the level of confidence we want, which corresponds to different alphas, which would correspond to needing to use different z-scores. So we will freeze everything with dollar signs except for the cell reference for that z-value. So we then hit enter and we copy these down. Now, one thing in Excel, I know the upper bound is the exact same equation, right? So it's the exact same equation, but instead to get the upper bound, I will add this margin of error to my sample mean so that I can then get the upper bound. So I'm going to show you probably the easiest way to do this. I'm just going to right click after I select what's in the cell and hit copy. And then I'm going to hit enter. When I want to paste it here, I know if I dragged it over, all my cell references wouldn't be right because the z-value would update one. So what I would then do is, if you click on this cell, if you go up here to this formula bar, or you can right click in this cell and hit paste, or you can click up in this taskbar and hit paste. Now I've got the exact same thing that was in there, so hopefully if I hit enter, I'll get the exact same value, right? I'm just copy and pasting it over. Sure enough, I do. But to get my upper bound, the one thing I need to change is, oh yeah, I'm adding that margin of error. All right, so all I have to do is copy and paste that over. I can't drag it, copy it. I have to copy and paste, and then change the negative sign to a positive sign. Now I just copy that down, and it updates it and does it for each of these different levels of confidence. So that's how we would construct the lower and upper bound in Excel. I want to get used to this so that we can look at different levels of confidence. Also, once we get to having proportions, it'll be a little bit different. So if you try to build in or use the built-in confidence equation, I think it's something like confidence.norm. It doesn't give us exactly what we want in terms of the lower and upper bound. And so this is how we have to construct our lower and upper bounds. Okay? We can do the exact same thing for proportions. Right? Now, in fact, if I delete those cells and I try to build this, I still am using, for sample proportions, the normal distribution. Right? I still want the same areas outside of my confidence interval for the 90, 95, and 99%. So it's really exactly what we just did before. We'll take that alpha. We know there's an area to the left, an area to the right, so we'll have to divide by 2. Right? There's 0.1 total outside the confidence interval. 0.05 is on the right, 0.05 is on the left. We'll hit enter. What did I forget to do? I forgot to take the absolute value. So I can use the absolute value function, but because this is a symmetric distribution, another nice way we can do this is just 1 minus, right? And that should, sure enough, give us the correct z-value. So when you're looking at these z-values for the confidence levels of 90, 95, 99, you should always find the same values. If you want the same area and you're going to a standard normal distribution, you'll always find the same 3 z-values. If we're looking these up by hand in the table, we round them to 1.65, 1.96, 2.58. We'll start seeing these show up a lot as we're doing confidence intervals and hypothesis testing. So now we want to build the lower bound for this sample proportion. Well, I've got my sample proportion up here. That's what I'm going to construct my confidence interval around. So to get the lower bound, I will subtract my margin of error. My margin of error is now this z-value, but multiplied by the standard deviation of my sample proportions. Okay? So to get the standard deviation of my sample proportions, so we're going to multiply it by that, I actually would take the square root of whatever the sample proportion I found was, times 1 minus whatever that sample proportion was, and then divide by my sample size. So I'm just using Excel to do the math for me. I could do this by hand in the calculator, but I've got all these numbers here. I can get really exact in Excel, and I think it's easier if we're just clicking on the values instead of typing them all in. So just like before, this is fine, but when I copy this down, I want it to update to instead of for the 90, for the 95 and 99% confidence interval, I want it to update to the different z-values I need. So I want this cell reference to update because that's what's referencing my z-value, but all the other references, right, the sample proportion and the sample size I took aren't going to change. So I put $signs around all the other cell references to freeze those. I hit enter. I now copy this down, and I've got my lower bound. Right? Now if we think about, like I mentioned in the, as I was looking through the PowerPoint slides, as we want larger levels of confidence, it should be that our confidence intervals are getting wider. Right? If I want to say something with 90% confidence, I want to say, I can tell you that the population mean with 90% confidence is within 5 and 10. Well, in order to tell you that it was in a certain range with 99% confidence, I have to include more values. So instead of 5 to 10, it might be, I don't know, 0 to 15. Right? So that confidence interval will get wider. So sure enough, our lower bounds should be getting lower, our upper bounds should be getting higher. So that's one way we can check. So just like we did before, how do I now get my upper bounds? Well, it's the exact same equation here. So I'll copy this, hit enter, go over to this cell, paste. Now I've got the exact same equation, right? So it should be in the exact same value. But for the upper bound, I don't want to subtract my margin of error. I want to add my margin of error. So I hit enter. I drag this down, and now I've got my upper bounds for this as well. So that's how we start to construct these confidence intervals when we have sample means where we know the population variance, or we have sample proportions. Now this is kind of a weird scenario. We usually don't know the population variance. And usually I wouldn't want to be constructing it from data. I was just doing this to show you an example. It's more likely that this is going to be given to you. So in an Excel assignment, I would, if I had an example like this, I might tell you what the variance is. Right? I'll give you the population variance. If you're ever doing work in Excel, it's likely you don't know what that population variance is. So instead, it's a lot more likely that we have an unknown population standard deviation. So I have another example here where you can find a sample proportion, just to give you some more practice if you want to look through these or try to reconstruct these. It's just like we did over here. But instead, the variable now is for the proportion of people in this data set that were white or non-white. Right? We want to know the demographic breakdown maybe of a sample that we took. Because we talked about we want to make sure it matches the population. So, got this 1, 0 variable to find the sample proportion. I would just take the average of it. And then everything down here, it's the same equations. I just our values are in different cells in terms of my sample proportion isn't in the same cell that it was on my other worksheet. But notice we find the same 3 z-values because when we're looking at sample proportions, we know that the sample proportions will be normally distributed. Right? And so when I turn these into, when I'm looking at z-values, that's a standard normal distribution. Okay? Now, the one problem that we have, that we talked about, or I talked about over the slides, was that we usually don't know the population variance, right? Usually we only have a sample variance. So up here, I found, okay, what's the average height from this sample of what? Using that count function, I found the sample size of that variable for how many observations I had of recorded height. So 36,000 people in the sample. I've got a sample mean of 64, and then I found the sample variance of that height as well. So to construct the confidence interval when I don't know the population variance, I can't use that standard normal distribution, because when I create, right, when we were creating the standard deviation for our sample means, that was where we took the square root of the original data's population variance over the sample size. Well, we don't have the population variance anymore, and so the best we can do is use the sample variance. But the sample variance has divided by n minus 1. So as n gets larger, that won't matter as much, but if we had smaller sample sizes, then our sample variance isn't going to be a very good, accurate representation of what the population variance is. And so when we convert these into z-scores, they won't really be standard normally distributed. They'll have a mean of 0, but they won't have a variance of 1. So instead, we've got these student t-distributions. At every single sample size, there's a different student t-distribution. So how can I find those? Well, let me delete this first. It's the same sort of setup. It's just now we have to use a different distribution. So instead of the norm.s.inv, right, because alpha is the area outside of my confidence interval, so there will be half of alpha on each side. Okay. So I typically would use norm.s.inv and then divide alpha by 2. I can't do that now because I need to use the student t-distribution, which instead of norm.s for standard normal, we use the t for student t. So t.inv, the probability or the area that we want on each side of our confidence interval will be alpha divided by 2. We then have to tell it our degrees of freedom. That was one thing we didn't need when dealing with the standard normal distribution that we need for the student t, because I said there's multiple student t distributions. Each sample size would have its own student t distribution, and so we need to tell it the degrees of freedom. And our degrees of freedom is simply the sample size minus 1. Okay? Now, similarly as before, we've got a problem, right? So we just want the value, so we'll take the absolute value here. And now we're getting the absolute value of that t value. Now notice, with a really high sample size, our z value is really close to the value we'd find from the student t distribution as well. It's a little off, but really close. Right? If I played around with the sample size a little bit, like let's say only had 35, notice that difference grows. Right? So I don't want it to be 35, so I'll undo that. Now I want to copy this down. So just like before, I want the alphas to update, but now I have to worry about, oh yeah, I'm using the cell reference for the sample size here, and that's not going to change, that's going to stay in the same place, so I don't want that to update as I copy this down. So I hit enter, copy this down. I now need to construct my lower bounds, so my confidence interval, just like before, it's built around the sample mean that I found. So I will then subtract that margin of error. So I'll take the t value now, instead of the z value like we did before, multiply by the square root of the sample variance I found divided by the sample size. Now, what this represents is the standard deviation of my sample means, given this sample size that I took. So, just like before, I want everything to update except this t value. I want to, sorry, I said that backwards. I want nothing to update except for the t value here. So I put dollar signs in front of every other cell reference. Oops. I then hit enter, and I can copy this down. Now notice, it doesn't change very much because we have a pretty high sample size here, which is going to force that margin of error to be pretty small. So when we're adding and subtracting, it's not changing that margin of error as much. Now we're pretty much done, because just like before, we know the upper bound will be the exact same thing as the lower bound in terms of the equation we'll use, except instead of subtracting that margin of error, we'll add it. So I go over here and I paste it. I then say, okay, I don't want to subtract the margin of error. I now want to add it. So I've now got my upper bound. I copy this down. We're good. Notice the upper bound is still getting larger as I want to say things with high levels of confidence. The lower bound is getting kind of lower, so this confidence interval is getting wider when I want to say things with higher levels of confidence. Okay. Now I have a whole other example here. I had some drug death data, and you can kind of look through this. If you have any questions, please feel free to ask me. I won't do a tutorial on this, but just another example of how we would construct confidence intervals. So here, I did this for 2 different years, right? So we might want to be able to compare 2 different time periods and say, well, were drug deaths higher in one time period than they were in the other? So I did 2012 data. So I found the mean. I went down here, and this was my 2012 observations. I then, for the 2016, found my sample mean drug deaths per capita, or per 10,000 people, in 2016. So I've got my 2 samples. I believe these are not Indiana counties. No, maybe it wasn't Indiana counties. I think it might have been Ohio counties. Regardless, I then can construct these confidence intervals, and so with 90% confidence, notice that the number of drug deaths in 2012 compared to the confidence interval for the number of drug deaths in 2016, they overlap quite a bit, right? So I can't say with certainty that drug deaths were higher in 2016. I want to give you an example of what happened, what would be an example of if they didn't overlap. Well, let's think about if this was 3.2 and this was 4.1. Well, now, the lowest value I could see in the confidence interval for 2016 deaths would be 3.2. The highest I could see for the 2012 deaths would be 2.7. So there, with 90% confidence, I could say, well, yeah, the true mean for drug deaths in 2016 actually is higher than in 2012, right? But if they overlap, like they actually did, right, 2.13 is below the highest possible value for 2012. 2.13 is less than 2.79. So between those 2 values, the 2012 and 2016 means could be anywhere in there. So I don't know which one is higher than the other based off of the samples that I took. Right? Okay, this is the confidence interval tutorial for this week. Should help you with the Excel homework. You should be able to work through that Excel homework entirely with what I've done here, with the exception of the last 2 problems will be some hypothesis testing, which we'll do next week. So the first 3 questions, you should be able to do everything based off of this tutorial, and I'll probably reference this a little bit when I'm looking at in corresponding to you on the Canvas announcements and things like that.